Hi Bob, I've been reviewing some quantum computing papers from April 2025, and there seem to be several interesting developments across different areas. I'd love to get your thoughts on the key advancements. What stood out to you from the recent publications?
Hello, Alice. April 2025 was indeed a productive month for quantum computing research. I noticed several important themes emerging. There were significant advancements in quantum error correction and fault tolerance, improvements in algorithm efficiency, practical applications in various domains, and interesting developments in quantum networking and cloud infrastructure. Which area would you like to explore first?
Let's start with quantum error correction, since that seems fundamental to practical quantum computing. I noticed a paper by Harper et al. About characterizing failure mechanisms in error-corrected logic gates. Could you explain their key findings and why they matter?
Great choice. Harper et al.'s paper is quite significant. They used a heavy hex code on superconducting qubits to investigate how different noise sources impact error-corrected logic. Their key finding was that idling errors during readout periods severely affect quantum memory performance. They demonstrated substantial improvements by designing a low-depth syndrome extraction circuit. They also conducted a stability experiment to understand how readout assignment errors affect logic gates, revealing a trade-off. Additional stabilizer readout cycles improve error rates, but increase memory decay time. Most importantly, they identified that measurement noise is the dominant factor affecting logical gate performance. This work is valuable because it gives us practical insights into optimizing error correction for real quantum hardware.
That's fascinating. Speaking of error correction, I also came across another paper by Lee et al. About autonomous quantum error correction. They claim to have beaten the break-even point. Could you explain what that means and how their approach differs from conventional QEC?
Yes, Lee et al.'s paper represents a significant breakthrough. The break-even point in quantum error correction refers to the threshold where a logical qubit protected by QEC lasts longer than the best physical qubit in the system. What makes their approach revolutionary is that they've implemented autonomous QEC using a single trapped ion, encoding the logical qubit in multiple internal spin states rather than using multiple physical qubits. Their method eliminates the need for measurement and feedback, which are typically required in conventional QEC. Instead, they use engineered spin-motion couplings to transfer error-induced entropy into motional modes, which are then dissipated through sympathetic cooling with an ancilla ion. This approach extended their logical qubit lifetime to approximately 11.6 milliseconds, substantially outperforming both the physical qubit, otherwise 0.9 milliseconds, and uncorrected logical qubit, about 0.8 milliseconds. This is groundbreaking because it demonstrates error correction without the overhead of measurement and feedback, potentially offering a more efficient path to fault-tolerant quantum computing.
That's remarkable. It seems like there's also interesting work happening in formal verification of QEC. I noticed Huang et al. Propose a framework called VariQC. How does their approach help ensure the correctness of quantum error correction implementations?
You're right to highlight Huang et al.'s work on VariQC. Formal verification is crucial for ensuring that QC implementations actually do what they're supposed to do. Their paper introduces a specialized assertion logic and program logic specifically designed for QC programs, with a sound proof system. What's particularly clever about their approach is how they handle verification conditions, VCs, for poly errors. They reduce VCs to classical assertions that can be solved by SMT solvers, and for non-poly errors, they provide a heuristic algorithm. They've formalized this in the cockproof assistant, creating what they call a verified QC verifier. They've also implemented an automated verifier called VariQC for verifying various fault-tolerant scenarios. The significance is that as quantum error correction becomes more complex, formal methods like this will be essential to ensure implementations are correct before deployment on expensive quantum hardware. They demonstrated this by verifying 14 different stabilizer codes, showing the framework's broad applicability.
That makes a lot of sense. Moving to a different topic, I'm curious about the advancements in quantum circuit optimization. There seems to be growing interest in using evolutionary algorithms for this purpose. Could you explain the approaches in Sunkel et al.'s paper on hybrid evolutionary algorithms and how they compare to Kohle et al.'s work on mutation techniques?
Both papers tackle quantum circuit optimization using evolutionary algorithms, but with different focuses. Sunkel et al. Propose a hybrid evolutionary algorithm, specifically for minimizing circuit depth. They evaluate two variants, one combining an evolutionary algorithm with an optimization subroutine to optimize rotation gate parameters, and another relying solely on evolutionary operations, mutations and crossover. They approach the problem from two angles, constructing circuits from scratch with random initializations, and starting with a target circuit to optimize further. Their experiments on 4 to 6 qubit circuits showed significant depth reductions while maintaining high fidelity. In contrast, Kohle et al. Focused specifically on mutation strategies within genetic algorithms for quantum circuit synthesis. They analyze how different mutation types transform circuits and identify which strategies enhance efficiency and performance. Their experiments used a fitness function that balanced fidelity with circuit depth and T operations. Their key finding was that combining delete and swap strategies outperformed other approaches for circuits with 4 to 6 qubits. The main difference is that Sunkel's work examines the overall hybrid evolutionary framework, while Kohle's paper drills down specifically on mutation operations. Both contribute valuable insights for developing more efficient quantum circuit optimization tools, which is crucial for NISQ-era quantum computing.
Thanks for that comparison. I also noticed an interesting paper by Taigen et al. About QAOA-GPT, which seems to use generative AI for quantum circuit generation. How does this approach differ from the evolutionary methods, and what advantages might it offer?
QAOA-GPT represents a fascinating shift in quantum circuit design methodology. Unlike the evolutionary approaches we just discussed, which iteratively improve circuits through selection and mutation, Taigen et al. Leverage generative pre-trained transformers, GPT, to directly synthesize quantum circuits for solving optimization problems, specifically focusing on max-cut problems on graphs. The key innovation is training the GPT model on a synthetic dataset generated using adaptive QAOA, a method that incrementally builds problem-specific circuits. Once trained, QAOA-GPT can generate high-quality circuits for new unseen problem instances without requiring the computational overhead of classical optimization or gradient evaluation. The advantages are significant. First, it dramatically reduces the classical computational overhead typically required for QAOA circuit generation and parameter optimization. Second, it generalizes well to new problem instances. Third, it can potentially generate more compact and efficient circuits than traditional methods. This approach represents a shift from algorithmic circuit design to learning-based circuit design, which could be particularly valuable as quantum hardware scales up. While evolutionary methods excel at optimizing existing circuits, QAOA-GPT can generate entirely new circuits tailored to specific problems with minimal overhead. This work suggests that generative AI could become a powerful tool for scalable quantum circuit design, potentially complementing evolutionary approaches in a comprehensive quantum compiler toolchain.
That's really interesting. I'd like to shift gears to quantum cloud computing. Zhou et al. Introduced CloudQC, which seems to address multi-tenant distributed quantum computing. What problem are they solving, and how does their approach differ from previous work?
Zhou et al.'s CloudQC paper addresses a critical gap in distributed quantum computing, DQC, research. While DQC allows large quantum circuits to be executed across multiple quantum processing units, QPUs, previous work hadn't addressed the challenges of running DQC in a multi-tenant environment, essentially a quantum cloud where multiple users are executing circuits simultaneously. CloudQC is the first framework to tackle two key problems in this context: how to place multiple quantum circuits onto QPUs efficiently, and two, how to schedule network resources to complete these jobs optimally. The framework includes two main components: a circuit placement algorithm and a network scheduler, both designed to optimize quantum network cost and job completion time. What makes their approach novel is its network awareness. They explicitly consider the topology and constraints of the quantum network connecting QPUs, which is crucial for distributed quantum execution. Previous DQC work typically focused on single circuit placement without considering network resource contention among multiple users. Their experimental results, using real quantum circuit workloads, showed that CloudQC significantly reduces average job completion time compared to existing DQC placement algorithms, both for single-circuit and multi-circuit scenarios. This work is important because as quantum computing scales up, cloud-based multi-tenant environments will become the dominant access model, similar to classical cloud computing today.
That makes sense. There also seems to be related work by Poryusef et al. On network-aware scheduling for remote gate execution. How does their approach complement CloudQC, and what specific aspects of quantum networking do they address?
Poryusef et al.'s work nicely complements CloudQC by focusing specifically on entanglement scheduling strategies in modular quantum computing networks. While CloudQC addresses the higher-level problem of circuit placement across multiple QPUs, Poryusef et al. Drill down into the network layer, examining how to schedule entanglement generation between QPUs efficiently. They evaluate two entanglement scheduling strategies, static and dynamic, under realistic conditions including probabilistic entanglement generation, limited communication qubits, photonic switch reconfiguration delays, and topology-induced contention. These are practical constraints that would affect any distributed quantum computing platform. Their key finding is that dynamic scheduling consistently outperforms static scheduling in scenarios with high entanglement parallelism, especially when network resources are scarce. They also investigate the impact of communication qubit coherence time, modeled as a cutoff for holding EPR pairs, showing that aggressive look-ahead strategies can actually degrade performance when coherence times are short. The complementarity with CloudQC is clear. CloudQC optimizes the placement of circuits across QPUs, while Poryusef's work optimizes how those QPUs communicate with each other through entanglement. Together, these papers address different layers of the quantum cloud stack, CloudQC at the application/placement layer, and Poryusef at the network/communication layer. Both are essential for building efficient quantum data centers that can support multiple users running complex quantum algorithms.
I see how these papers complement each other in the quantum cloud ecosystem. Now, I'd like to ask about quantum security. Pfefferman et al. Discuss hardness assumptions about learning quantum circuits and their cryptographic applications. What are the key insights from their paper?
Pfefferman et al.'s paper makes a significant contribution to quantum cryptography by establishing concrete hardness assumptions about learning random quantum circuits as a foundation for secure quantum cryptographic primitives. Their key insight is that if learning or cloning the output state of a random quantum circuit is computationally hard, which they argue is a reasonable assumption, then this hardness can be leveraged to build several important cryptographic tools: one-way state generators, OWSGs, digital signature schemes, quantum bit commitments, and private key encryption schemes. What's particularly notable is that these constructions don't depend on the existence of one-way functions, which are the foundation of most classical cryptography, but remain unproven. Instead, they rely on the inherent hardness of learning quantum states, for which they provide both theoretical evidence and black box lower bounds. The paper also addresses practical implementation by discussing noise-tolerant versions of their OWSG and digital signature constructions. These could potentially be implemented on near-term noisy quantum computers connected by a quantum network, while still remaining secure against noiseless quantum adversaries. This raises the intriguing possibility of useful cryptographic protocols that can run on NISQ devices. This work establishes important connections between quantum learning theory and cryptography, suggesting that many of the rich interconnections between these fields in classical computing extend to the quantum setting as well. It's a significant step toward practical quantum cryptography that doesn't require fault-tolerant quantum computers.
That's fascinating. Speaking of quantum security, I noticed several papers on post-quantum cryptography, PQC, including ones by El-Nasseri et al. And Conti et al. How do these papers address the challenges of implementing PQC in resource-constrained environments?
Both papers address crucial challenges in implementing post-quantum cryptography, PQC, in resource-constrained environments, but with different focuses. Al-Nasseri et al.'s paper provides a comprehensive analysis of the hardware complexity of PQC in embedded systems. They categorize PQC algorithms into families based on their underlying mathematical problems: lattice-based, code-based, hash-based, and multivariate isogeny-based schemes. Each family has distinct computational, memory, and energy profiles, making them suitable for different use cases. They discuss optimization strategies like pipelining, parallelization, and high-level synthesis to improve performance and energy efficiency. They also conduct a detailed complexity analysis of crystals Kyber and Macaleese, comparing their key generation, encryption, and decryption processes. Conti et al.'s paper introduces PQCAN, a modular framework specifically for simulating PQC algorithms in automotive systems using the Controller Area Network, CAN bus. They focus on the automotive domain as a case study, where embedded systems have limited computational capabilities, high traffic, and real-time response requirements. Their simulation enables adjustment of embedded system computational capabilities and CAN bus bitrate constraints. They analyze trade-offs between security levels and overhead for key encapsulation and digital signatures. The key difference is that Al-Nasseri et al. Provide a broader analysis of PQC in embedded systems generally, while Conti et al. Focus specifically on automotive applications with the CAN bus. Both highlight that implementing PQC in resource-constrained environments requires careful consideration of computational capabilities, memory constraints, and energy efficiency. These papers are important because as quantum computers advance, transitioning to quantum-resistant cryptography in embedded systems becomes increasingly urgent.
Thanks for that comparison. Let's switch to quantum machine learning. Tiplius et al. Proposed a Hamiltonian classifier that seems to address some efficiency challenges. What's innovative about their approach, and how does it compare to traditional quantum machine learning methods?
Tiplius et al.'s Hamiltonian classifier represents a significant innovation in quantum machine learning, QML, that addresses one of the field's most persistent challenges, the high cost of encoding classical data into quantum states. Traditional QML approaches typically require encoding dense vector representations onto quantum devices, which is resource-intensive and often limits scalability. The Hamiltonian classifier takes a fundamentally different approach by mapping inputs to a finite set of polystrings and computing predictions as their expectation values. This elegantly sidesteps the data encoding bottleneck. The paper introduces two classifier variants with different scaling properties in terms of parameters and sample complexity. Their approach achieves logarithmic complexity in both qubits and quantum gates, making it substantially more efficient than conventional QML methods that often require resources scaling linearly or worse with input size. When evaluated on text and image classification tasks against established classical and quantum models, their method delivered performance comparable to or better than these approaches. This is remarkable given its reduced resource requirements. What makes this work particularly valuable is its practicality for near-term quantum devices. Many QML papers demonstrate theoretical advantages or work with toy datasets, but the Hamiltonian classifier's efficiency makes it well-suited for large-scale, real-world applications even on NISQ-era hardware. By addressing the data encoding challenge, this approach could help bridge the gap between theoretical QML proposals and practical implementations that can handle real-world data volumes.
That's a really interesting approach. I also noticed a paper by Rath and Date comparing different continuous variable quantum encoding techniques for machine learning. How did their findings relate to the Hamiltonian classifier approach? And what insights do they provide about quantum data representation?
Rath and Date's paper complements the Hamiltonian classifier approach by exploring a different aspect of quantum-enhanced machine learning: how continuous variable quantum computing (CVQC) encodings can improve classical machine learning models, while Tiplius et al. Focus on a new classification method that minimizes quantum resources. Rath and Date investigate how quantum encoding techniques, specifically displacement encoding and squeezing encoding from CVQC, along with IQP encoding from discrete quantum computing, can enhance feature expressivity for classical models like logistic regression, SVMs, KNN, and ensemble methods. Their key finding is that CVQC-based encoding methods significantly improve classification accuracy and F1 scores, especially for high-dimensional and complex datasets. However, this comes with varying computational costs depending on encoding complexity and model architecture. The relationship to the Hamiltonian classifier is interesting. Both approaches seek to bridge quantum and classical computing for machine learning, but from opposite directions. The Hamiltonian classifier brings classical data into the quantum domain efficiently for quantum processing, while Rath and Date explore how quantum encodings can transform classical data to make it more amenable to classical processing. Their work provides important insights into the trade-off between quantum expressibility and classical learnability. It suggests that even if full quantum computers aren't available, quantum-inspired encodings can still provide benefits for classical machine learning. This represents a pragmatic middle ground in quantum machine learning, using quantum principles to enhance classical methods rather than replacing them entirely.
That's a really helpful comparison. There's also a survey paper by Zhang and Zhou on quantum transformers. What key approaches and challenges do they identify in this emerging area?
Zhang and Zhao's survey provides a comprehensive overview of quantum transformers, which represent a significant frontier in quantum machine learning. They identified two primary approaches to developing quantum transformer models. 1. Parameterized quantum circuit (PQC)-based transformer models. These are the main focus of current research and are compatible with NISQ devices. They employ various quantization strategies including QKV-only mapping, quantum pairwise attention, quantum global attention, and quantum-assisted acceleration. These approaches show promise in small-scale tasks by reducing complexity or enhancing performance. 2. Quantum linear algebra (QLA)-based transformer models. These rely on future fault-tolerant quantum computing and use techniques like block encoding and quantum singular value transformation to achieve efficient matrix operations with significant theoretical complexity reductions. However, these remain largely theoretical. The survey highlights several key challenges: limited scalability of current approaches, absence of standardized testing benchmarks, the barren plateau problem during training, where gradients vanish exponentially with system size, hardware constraints of NISQ devices. For future research, they recommend prioritizing optimizing PQC-based hybrid architectures and quantum global attention models, establishing unified evaluation frameworks, addressing training difficulties, exploring hybrid PQC-QLA approaches. This survey is valuable because it maps out the landscape of quantum approaches to transformers, currently the dominant architecture in classical AI, and provides a roadmap for researchers working to achieve quantum advantages in this domain. The field is still nascent, but the potential to leverage quantum parallelism and entanglement to overcome classical transformer limitations is significant.
Thanks for that overview. Let's discuss quantum algorithm efficiency. Mizuta and Kuwahara's paper on Trotterization for low-energy states seems to offer significant improvements. Could you explain their main results and why they matter?
Mizuta and Kuwahara's paper represents a significant theoretical advancement in quantum simulation, particularly for condensed matter physics and quantum chemistry applications where low-energy states are of primary interest. Trotterization is a fundamental technique for implementing quantum simulations on quantum computers, breaking down complex Hamiltonian evolution into sequences of simpler operations. The authors tackle a long-standing question: can we leverage the properties of low-energy states to make trotterization more efficient? Their main result is proving an optimal error bound for trotterization when applied to low-energy initial states. For generic local Hamiltonians composed of positive semi-definite terms, they show that the trotter error is at most linear in the initial state energy delta and polylogarithmic in the system size n. This translates to substantially reduced computational cost for low-energy states, with delta and current of ONG compared to arbitrary initial states where G is the energy per site. What makes this result particularly important is that it achieves the theoretically best scaling in the initial state energy delta. Previous work had shown some improvement for low-energy states, but these benefits rapidly vanished as the trotter order increased. Mizuta and Kuwahara resolve this problem, showing that the advantage persists even at higher orders. They also extend their results to weakly correlated initial states with low energy expectation values, even if they're not strictly in the low energy subspace. This work matters because it enables more efficient quantum simulations, specifically for the states most relevant to physics and chemistry applications. By reducing the resources needed for accurate trotterization, it brings practical quantum advantage for these applications closer to reality on near-term quantum hardware.
That's really insightful. I've also noticed several papers about applying quantum computing to specific domains, like Osaba et al.'s work on package delivery optimization and Woodman et al.'s paper on reinsurance optimization. How mature are these applications, and what benefits do they demonstrate over classical approaches?
Both papers represent interesting applications of quantum computing to optimization problems in different domains, though they're at different levels of maturity and demonstrate different types of benefits. Osaba et al.'s paper on package delivery optimization builds on their previously published quantum classical technique called quantum for real package delivery, Q4RPD. They focus on addressing realistic constraints in vehicle routing problems, simultaneous pickup and deliveries, time windows, and mobility restrictions by vehicle type. Their paper is primarily a demonstration of these features across 7 problem instances. This work is relatively mature in terms of formulation, but still represents a hybrid approach where quantum computing assists with specific components of the optimization rather than solving the entire problem. The benefits are more about handling complex real-world constraints rather than demonstrating a clear quantum advantage over classical methods. Woodman et al.'s paper on reinsurance optimization takes a dual approach. They implement a practical simulated annealing optimizer that handles realistic constraints for catastrophe excess of loss reinsurance contracts, while also exploring the potential of quantum branch and bound for future applications. Their simulated annealing approach effectively generates contract structures within complex constraints, proving useful for treaties with multiple local optima. However, their branch and bound formulation reveals that solving the full problem with current quantum computers would require substantial hardware improvements. Their work is more mature on the classical side, with the quantum component being more exploratory and forward-looking. Neither paper demonstrates a clear quantum advantage over classical approaches at this stage. Instead, they lay groundwork for potential future advantages by carefully formulating domain-specific problems in ways that could leverage quantum capabilities as the hardware improves. This reflects the current state of quantum applications. We're still in the phase of identifying and formulating suitable problems, rather than demonstrating definitive quantum advantages in practical settings.
That makes sense. Before we wrap up, I'd like to get your thoughts on the future outlook for quantum computing based on these April 2025 papers. What trends do you see emerging, and what areas do you think will see the most progress in the coming years?
Based on the April 2025 papers, I see several important trends emerging. 1. Practical error correction. Papers like Lee et al.'s autonomous QEC and Harper et al.'s characterization of failure mechanisms show we're moving from theoretical QEC to practical implementations that work on real hardware. The focus is shifting toward resource-efficient approaches that can function in noisy environments. 2. Quantum classical integration. Many papers demonstrate a pragmatic approach of combining quantum and classical techniques, rather than pursuing pure quantum solutions. Examples include the hybrid evolutionary algorithms for circuit optimization, QAOA-GPT's use of classical ML to generate quantum circuits, and quantum-enhanced classical ML methods. 3. Hardware-aware algorithms. Papers like Lang et al.'s on CMOS-Compatible qubit fabrication and Sun et al.'s hardware-guided qubit mapping show increasing awareness of real hardware constraints in algorithm design. 4. Quantum cloud infrastructure. The emergence of papers on multi-tenant quantum computing, CloudQC, and network-aware scheduling indicates that distributed quantum computing infrastructure is becoming a serious research focus. 5. Domain-specific applications. We're seeing more targeted applications in fields like finance, logistics, and ecology rather than general-purpose algorithms. Looking forward, I expect the most progress in 1. Error mitigation and correction. This remains the fundamental enabler for all other quantum applications. 2. Quantum machine learning. The diversity of approaches, Hamiltonian classifiers, quantum transformers, etc., suggests this field is rapidly evolving. 3. Quantum network protocols. As quantum networks become reality, we'll see more work on protocols for distributed quantum computing and quantum communication. Verification and validation. As quantum systems grow more complex, methods to verify their correctness will become increasingly important. 5. Hardware-software co-design. The papers show increasing recognition that quantum advantages will come from tight integration between hardware capabilities and algorithm design. Overall, the field appears to be maturing from theoretical proposals to practical implementations, with increasing focus on real-world constraints and applications.
Thank you, Bob. This has been an incredibly informative discussion. It's fascinating to see how quantum computing research is progressing across so many fronts simultaneously, from fundamental improvements in error correction and circuit optimization to practical applications and infrastructure development. I particularly appreciate